Good afternoon, everyone, and welcome to ISPE's quarterly webinar program. Today's presentation is Acoustical Materials to Reduce Vehicle Noise from the Past to the Future, presented by Pranab Saha. My name is Emily Widener, ISPE's Education Specialist. I will be your moderator for today. I'd like to go over a few things before we begin. All attendees have been muted to avoid audio feedback issues. All questions will be held until the end of the presentation. To ask a question, please type it into the questions box throughout the program, and I will read them aloud at the end of the presentation as time permits. The slides for this presentation can be found in the handout section of the toolbar. You are eligible to earn PDHs by logging into this webinar for its duration, and you'll be receiving an email later today with your certificate. With that, I will go ahead and hand it over to Pranab.
Thank you, Emily, and good morning, everyone, in the time zone you are in. Today's presentation would be a blend of, I believe, something that's interesting and with technical, with noise, vibration, and harshness in the automotive industry. Acoustics has different meanings to different people. To someone, it is music or a part of an instrument or an event. To another person, it is an ambience or environment. Acoustics, in that sense, is something we like and we enjoy. On the other hand, there is something that's called noise. And here you can see the maximum noise, 70 decibels. And this is something we would like to avoid. Saying that, noise is subjective. If a tree falls in the forest and you are not there, is it noise? I will let the physicists worry about it, but we in the application field, engineers, or in technical fields, we better move on to the next thing. In the mobility industry, this is the horse-driven cart. None of us were there when these were very popular, but there is often a reluctance to accept something that is unknown. We know that today for sure, but even over 100 years ago when we were not there, people had challenges accepting something that is unknown, and some people were all excited because they are doing something that's very new, great, and has the potential to succeed. The mobility industry and the NVH industry are not too far from that, although the reasons could be somewhat different. The move from the horse-drawn vehicles to the automobiles was the same. Average people could not afford it. They were worried about the speed. They were worried if we can control the vehicle properly. But the people who were working on the internal combustion engines, or today working on electric vehicles, or tomorrow they'll be working on autonomous vehicles, they are all excited. We will try to touch base some of these if time permits, the EVs and the AVs that I mentioned, but we really need to know a little bit about the cars that we drive today and its noise. The vehicle construction from full frame to unibody. An acoustics engineer would love to have an 8-cylinder vehicle. And in an 8-cylinder vehicle, the combustion is very smooth. There is no roughness to that. And then on top of that, we have this full frame vehicle that the acoustics engineer love. That way, the chassis will have all the energy stored in the chassis. The body comes on top of the chassis, and that is connected by something called body mounts, where the body mount are nothing but isolators. It isolates and does not allow the vibration energy to go from the chassis into the body or inside the vehicle. So we don't have any vibration issues. All we have is sound, and the sound can be addressed by using something, as we call it, an absorber that absorbs the energy, or barriers that blocks the energy. That means once the sound is already in an environment, an absorber does not allow it to reflect off of hard surfaces. And from the engine compartment, the sound doesn't go to inside the vehicle because the barrier blocks that sound. So a full frame vehicle acoustically is easier to solve. The challenge is if we have an accident, the body doesn't have enough strength to sustain, to absorb that energy. So from safety purposes, unibody construction vehicles is much safer than a full frame vehicle, but it does not have the frame. The frame is gone. Therefore, all the vibration, all the exciting energies from the road, from the pavement, from other operations of the vehicle now goes through the connections and excites the floor pan, excites the door, excites the whole body. So we have all this vibration that we did not have in a full frame car all of a sudden. And that's where damping treatments come into the picture. In the acoustics industry, the damping material was not invented until the late 70s. In acoustics, we did have damping materials. That's not a problem. But the application did not call for using that in the vehicle. So now we are working on damping materials and many other materials, including the absorbers and the barriers we talked before. A little bit about vehicle noise sources. The moment I start the engine, we have propulsion-related noise. In an internal combustion engine, or we nowadays call it ICE, we have the engine noise, we have the transmission noise, we have cooling fan noise, we have air intake noise, and then we have exhaust noise. All of these things are related to the propulsion of the engine. If we talk about electric vehicles, we have the electric motor noise, we have the gear noise, and we have the inverter noise. Inverter is the device that transforms from AC to DC and DC to AC to be able to operate the vehicle properly. And then when I drive the vehicle, this portion is always the same, whether it's an ICE or an EV or an AV in future. So what we have is brake noise, we have road noise, we have tire noise, and we have wind noise. This is a typical vehicle, an internal combustion engine with different sources and things that we need to operate the vehicle. What I have shown here, besides the engine, the transmission, the cooling fan, and the exhaust, I've shown some of the other noises that are yellow highlighted because as the vehicle is being driven, we have the tire thump noise, with the frame squeak noise, we have road rumble, brake squeal, we have wind noise, HVAC blower noise, body rattle noise, and many other types of noises that you can think of. An acoustics engineer's responsibility is to make sure all of these are addressed. So inside the vehicle, the occupant, when driving the vehicle, finds it quiet, pleasant, and it's fun to drive. One of the things we need to know if we're going to solve these noise issues is called frequency. The audible frequency is between 20 to 20,000 hertz. We don't hear the same at all frequencies. We don't hear at very low frequencies, close to 20 hertz, 30 hertz, 40 hertz or so. Neither do we hear that much above 10,000 hertz. Yes, different people's hearing capabilities are different, but in the vehicle industry, we normally look from about 30 or 50 hertz to about 10,000 hertz. In an ICE, the moment I start the engine, what is happening is inside the engine block, there's a combustion. And if I rub the engine, depending on the number of cylinders, depending on the RPM, that corresponds to a particular frequency, and we call induction noise. If you accelerate very fast at a very short period of time, it goes from a low frequency to a high frequency. The reason for that is it's going from about idling speed of 900 RPM to about 3,000, 4,000, 5,000 RPM at a very short time. So you hear those growling sounds that we don't necessarily like in a very expensive, pleasant car. In a sports car, the things are totally different. I would like to hear that sound. So, depending on the type of vehicles we are working on, the acoustics engineer may want to de-emphasize this induction noise in the car or emphasize in a different way so we can appreciate the sound and the speed and the character of the vehicle. We are driving our vehicle on a smooth asphalt road and then on a coarse road. Below 500 hertz, most of the noise that you hear, besides that engine noise that I was mentioning, would be the road noise, or we call the coarse road noise. Somewhere between 400 to 4,000 hertz, we have the engine and its accessory noise. This is now the actual combustion noise, not the air induction related noise. I'm driving my car at about 45 miles per hour. I hear tire noise. In order to be able to appreciate the tire noise, we have to drive the vehicle on a smooth asphalt road. I don't know the roads in Indiana, but in Michigan, where I live, our roads are everything but quote unquote smooth and paved. We have a lot of rumbles, a lot of roughnesses on the road, so we can hear the tire noise more. We can also hear the road noise more. As I accelerate, I hear noise from 2,000 hertz and up. That's the wind noise. And the wind noise could be due to the fact my vehicle is driven at 70 miles per hour. The wind from the other side is coming and hitting a blunt object at a relative speed of 70 miles per hour. That causes turbulence, and those turbulence waves, once it gets inside the vehicle, we hear the wind noise. Yes, today's vehicle bodies are more streamlined, more aerodynamic. They all essentially look the same, but nonetheless is still a blunt object, and the wind comes and hits at 70 miles per hour. If there are any other leaks, then the sound can get through those leaks to inside the vehicle. And then we have brake squeal noise. I'm driving my car. There's a car in front of me. I have to go and hit the brakes immediately. I slam on the brakes, and I hear the screeching sound at about 8,000, 7,000, 10,000 hertz. If we go to the EV for a few minutes, all these noises due to the road noise, tire noise, wind noise are there. The body thump is there. The body rattle is there. But the propulsion noises now are this electric motor, its noise. The electric motor may have an induction motor or permanent magnet motor. Depending on what kind of motors it has its own challenges, and that generates noise. Then we have gearboxes, because this motor is running at a high RPM, but we have to bring it down. It's a single stage gearbox, and that noise is horrendous. So we have to solve that noise. Then we have this inverter, because we have batteries. That is, batteries have to be able to transfer the energy into the motor, and this inverter, that when it switches, it has its noise. The noises of these three elements are different than what we have in the ICE. When the EVs came into the picture first, we thought there will be no noise. We are more concerned about people who are pedestrians, they are walking, would they be able to hear that an EV is coming? Well, that's one type of issue. But inside the vehicle now, the occupant, the owner of the vehicle, is finding that although the overall level of the noise is less, but its character is different. When I say character, its frequency contents are different that I've never seen before or never heard before. And therefore, what we are finding is, although the overall noise of the EV is less than ICE vehicles, but doesn't necessarily mean it's pleasant. We have to bring it down to a level that we like it. Therefore, there are a lot of challenges in working with the EV vehicles as well in terms of noise and vibration is concerned. In this case, the electric motor goes from a low speed to a high speed, and while it does that, it goes through all its different RPM. And just like in an ICE, there was induction noise, which usually lasts from 100 hertz to 250 hertz. In this case, for EVs, this can sweep from about 50 to 3,000, 4,000 hertz. So the type of solutions I'm going to have has to be able to address all of these frequencies based on what I need. This slide shows in a typical vehicle, and yes, in this case, it's an ICE, but it doesn't have to be ICE. We have different types of noise control treatments. Even in an EV, there is going to be an e-motor. Therefore, the e-motor is going to make some noise, and it does. And in the engine compartment, we have hood liners, we have engine side dash absorbers. Inside the vehicle, we have headliners. On the floor, we have carpet. And on the dash sheet metal, we have something called dash mat. And the seats can absorb sound. In the trunk, we have sound package materials and so on. I don't know how many of you in the audience today, where you are, have worried about the noise and vibration issues in a vehicle or noise and vibration in general. But now that you are seeing some of these parts, you possibly would be more attentive in future when you are driving your vehicle or riding a different vehicle and so on. How do we control the noise? Yes, there are powertrain engineers, there are propulsion engineers who are working at the source. They are trying to reduce the noise at the source. But there is also acoustics engineers who are working on the body of the vehicle or who are working on sound package materials. that means acoustical materials, to address the sound and the vibration issues in the vehicle. There are essentially 4 different elements, of which 3 of them are clearly noticeable, visible. One of them is called the absorption treatment, and I'm going to spend a little bit of time on each of these so you understand how they work. And in a real life, you may be able to find, even outside the vehicle, how they're working in your application. Then there is barrier treatment, there is damping treatment, and isolation treatment. In an absorption treatment, the sound energy is here in red. The sound rays come and hit on an absorption material, which is a porous material. It's a fibrous or cellular material. And then part of the energy reflects back, part of the energy goes inside. The material gets dissipated, loses its energy. In an application, the source and the receiver, they're both in the same place. An example, inside the car, there is some noise. The headliner, if it can absorb sound, it will reflect less sound back into the cabin. So the headliner can work as a good absorption material. The next one is a barrier treatment. The noise is coming, the red line. Yes, it can reflect back. Yes, it can get inside and dissipated, but also it can go through the material to the other side. So in this case, this is the engine compartment. Whether it's an ICE or e-motor does not matter. This is where the source is. The sound goes through the dash, goes inside the vehicle. The barrier blocks the noise. A barrier is an impervious material. It's like a door. So the door can block the noise. However, if in that barrier there are holes, that means underneath the door there's a big clearance. Then a lot of sound will go through the leaks and get to the other side, and it will not work properly. That means block the sound properly. Now, the damping treatment. My body vibrates. If I can vibrate at resonance, if I can put damping material, viscoelastic material, which works best at resonances, so it can reduce that vibration energy and I will get some smoothness, some pleasantness. Isolation treatment, that body mount that I mentioned before, is nothing but an isolator. It is between the source, vibration source, and the receiver, the vibration energy at the receiver side. So it could be between the engine and the cradle. It could be between the chassis and the body. It absorbs that energy and doesn't allow it to go through to the other side. So in a noise control system, we have a source. We can control the noise at the source. We have a path. This is the doghouse in a truck. The sound goes through the path, and this is the receiver where my receiver is sitting in the car in my vehicle. We want to do everything possible to make this person, keep this person happy so that the person can drive the vehicle without any other incidences going from point A to point B. This is a typical headliner, which could be an absorptive part. These are 2 examples of dash mat. On the left-hand side, it's a barrier decoupler system. On the right-hand side, it's a dissipative system. And at some point later, if I have the opportunity, I will explain a little bit. But the barrier decoupler means I have a barrier and I have an absorber. And the dissipative means 2 layers of absorption material working together to reduce the noise. These arrows you will find in some of the slides. They're a little bit important. that has to do something with the Q&A, just so you know. It is not in your handouts, though. Okay, a floor carpet. This is what you see from inside the cabin. This is the carpet piles. Your seats are mounted on top of that, and your feet are actually on this area. But if you ever reverse the carpet, on the underside, you may sometimes see there is a mass backing coating, a black colored coating material that is there purposely to block the sound. And then you will see some absorption materials, what we call is a decoupler materials. Again, to help block the noise as much as possible. How did we get from there to here? Up till now, the things that I have talked, those are more quantitative information. But then I do all this work. Do I like the sound? That's qualitative. That's subjective listening. We have been building cars for over 100 years. From day one, essentially, once we knew the car is running properly, we wanted to make sure what are the other things that we can do to make sure the sound is pleasant. So this is a slide on the left-hand side that shows some data have been recorded in a reel-to-reel tape recorder. I hope some of you know what a reel-to-reel tape recorder is. And now these are the people who are listening to that sound and judging if the sound is good, do I like it, or don't I like it? So I will talk a little bit about subjective listening from the past to now. We will talk a little bit about how we used to acquire data in the past. How do we do it today? On the right-hand side, this is the typical sound package treatment. It is taken from the floor. This is the carpet. This black lining material, that's the barrier on the back of the carpet. We call the backing. And this one is the decoupler or an absorption material. This is the floor pan. And this textured surface that you see, this is the damping material on the floor to reduce the vibration of the floor. In the old days, this is possibly in the 1950s. Some of you who can looking at the car, you may be able to figure that out also. There is a test car. This is my test car. I want to know the noise of that car, and this is my data acquisition car. In those days, we didn't have modern systems like we have a battery-powered digital recorder. We had 120 volts, reel-to-reel tape recorder. The problem is, if we have that tape recorder in this vehicle, how do I run that tape recorder? Because the vehicle has only 12 volt DC. The tape recorder needs 120 volts AC. So I have to have an inverter. That inverter makes noise. The tape recorder itself may make noise, and therefore all those noises will submerge, will not allow me to measure the noise of the car that I want to do. So we had two cars. I don't know if you can see this dotted line here, the dashed line. That's actually wire. So in the test car, there is a microphone, and that microphone cable is going to the back car. In this car, I have a tape recorder, I have an inverter, I have a person who is running that tape recorder to collect the data. So this is that tape recorder. This is that tape recorder. So the driver is in the data acquisition car, and the trailing car is going to drive that car, record the data. And remember, if the front car goes at 50 miles per hour, the back car cannot go different. They have to be synchronized. So that was a challenge to make sure that no other accidents happen, no other casualties take place. Then you come back, you play those tape recorders back, the signals back, and people are going to listen to that sound, just like I shown you 3 slides before. They're listening to the sound and subjectively judging if the sound is good or not. Today, this is not even today, this is possibly about 7 or 8 years ago, and today things have even changed further. This is an Aachen head or a binaural head simulating a person. In here, there is a microphone on this ear and on the other ear. And these are amplifiers and signal conditioners. They all run in batteries. So I can have all of that in the car, and the driver will sit on the other side so that the driver can drive the vehicle and acquire the data. Then we have blind jurors sometimes, because a lot of times if you are riding the vehicle and subjectively judging if the vehicle is quiet or not, the appearance of the vehicle may have some bias in your judgment. So we, from time to time, have blind jurors. Of course, today we would like to tape record everything, bring it back in the lab, and have someone listen to the sound. But about 20 years ago, 30 years ago, these were very common. This is the binaural recording. This is by one manufacturer called Head Acoustics. This is another set of binaural recording by Hottinger, Bruel, and Kerr. So in the binaural work in the auto industry, what can be done? You can generate some signal, and there's a microphone. It picks up the signal, and then it goes to the ear, to the signal processing, and it judges how good the sound is, how bad the sound is, and so on. And today's technology, we have taken the same concept into non-automotive area. For example, the cell phone that we have, this cell phone sound quality is important. So in this case, this is the cell phone which can be pressed closer to my ear or removed farther away from my ear by maneuvering this adjustment, this fixture, to simulate what is a best listening condition. A lot of times, if we make these measurements on the road, which we have to, because after all, the car buyer is going to drive the car on the road. But the problem of making noise measurements or many other measurements on the road is it depends on the environment. If it is too windy, I cannot make sound measurements because the wind noise is going to dominate, and the wind noise is not the wind noise of the vehicle, it's the wind noise of the environment. Okay. If it rains, I cannot make measurements because all the raindrops and everything else is going to come to the roof, is going to make noise that I cannot duplicate. So people make measurements on chassis roll dynamometers. This is possibly a slide taken some 60 years ago. One of the first, it could be 70, 80 years ago, one of the first chassis roll dynamometers, which was unfortunately an open air dynamometer at that time. So this is below that, and these engineers or technical people, they are operating the dyno, and the measurements are made in the vehicle. Today, this is a truck, a semi-truck, in a hemi-anechoic room. Hemi means half, ane means no, coic means echo. That means half the room where there is no echo or reflection. There we have chassis rolls. These are the rolls that you can see, and the vehicle can be driven inside the room. So even if outside it's raining, it's windy, as long as the inside is quiet, it doesn't matter. and I can make all those road noises and things like that. I can also make engine noise, and with some effort, I can also make wind noise measurements in a case like this. In the 1980s, a lot of journalists from New York City, from Washington State or Washington, D.C., they came to the Detroit area and wanted to know what is happening to the automotive industry, because the North American car companies, all of a sudden, in the late 70s, they dropped their quality. The Japanese car manufacturers, they have started bringing in cars to this country and selling them here. And as the quality dropped of our cars, those not Japanese cars and other foreign cars, they found their market almost immediately. And so the concern was, what is happening to the automotive industry of ours? At that time, also, we started working on active noise cancellation. My talk today is really with the passive noise cancellation, that means with barriers and absorbers. But I just wanted to mention that the sound of silence, the active noise cancellation, is very much there and is going to come back in the vehicles. Possibly would be more of a blend of a passive and active. This is, I don't know if you can sense what it is, but this is jute. At one time, we used to use a lot of jute under the carpet on the floor in our vehicles. This jute used to come from Bangladesh. At that time, it may have been part of India. This is before 1971, around 60s and so. So it was part of India, but that part is now in Bangladesh. They had cyclones. They have other natural disasters that the car companies here could not rely on the schedule of the shipping and receiving these parts, these materials to be used in a car. So we went to the southern states of our own country, in the Carolinas, in Georgia, in Alabama. There are a lot of cotton trees, the cotton industry. And we started using the cotton, we call that fiber pad. We call them needle cotton fiber pad or resinated fiber pad. That means all these fibers, cotton fibers, we mechanically connect them one with the other. And when we do that, we call it needling. And that's why it's called a needled cotton fiber pad. Or through some form of adhesive, we bond them one against the other. And that's what is called resinated fiber. The problem is this fiber pad, they did not meet the thickness and the surface density requirements that the car companies have prescribed. So what we have is the carpet is going to go on top of the fiber pad. If the fiber pad is thinner than what it's called for, the carpet is on top of that, there are wrinkles. You can see these wrinkles. Otherwise, in a very posh car, these wrinkles, they don't look good. Has nothing to do with acoustics, but has everything to do with the appearance, the marketing, the ambiance, and everything else. Therefore, although we switched from jute to fiber pad, that did not cut it. That did not work properly because it could not meet the thickness and density requirements. That gave the opportunity for the polyurethane foam industry to be able to mold the foam on the back of the carpet as a two-step process, but it's all one unit. It's not the carpet and the fiber pad separate. It's the carpet, the mass backing, and the foam decoupler, all one unit. That way the fit is great. I want to talk a little bit about dissipative systems. We are in the lightweighting mode. We want to reduce the weight of the vehicle. We started that from the early 70s, from the first time we had the oil embargo situation. At that time, we reduced the thickness of the steel as much as we could without compromising the safety of the vehicle. And today, we are trying to work with materials to see if we can reduce the weight of the materials. So, at one time, when we had this barrier decoupler materials, now from there, we are going down to dissipative systems. A dissipative system is a two different layers of fiber pad. The fiber pad could be needled cotton fiber pad, like I mentioned before, or the resinated pad, or in today's technology, it could be, we call BICO, that is bi-component fiber pad, which has polyester, polypropylene, which with heat is going to soften, melt, and you can mold those things. So there are two different layers of fiber pad with different airflow resistance, different characteristics, which can not only absorb sound, but also can block sound propagation through the material. Its ability is not as good as a barrier decoupler in order to block the sound, but overall, with all other treatments that we have in the vehicle, if they can provide an acceptable performance and reduce the weight, say 70%, 60%, than a barrier decoupler, that's a plus. So this slide was for the carpet. This is the one for the dash mat or the firewall that some of us call it, but we in the automotive industry like to call it a dash mat. This is a single layer of fiber pad, not two layers of fiber pad anymore, which is being used as a dissipative system with a scrim on top. And this has the potential to have the similar performance as a two-layer dissipative system. Now let's talk about electric vehicles a little bit. It's like draining the lake. Elimination of the IC engine dramatically reduces the powertrain-related noise like we have in the ICE. But as we reduce the powertrain-related noise, because the internal combustion doesn't exist, it seems like draining the lake. Other noises that were submerged in the same frequency range now become prominent. I mentioned before the road noise is below 500 hertz. A lot of that was masked by the internal combustion engine's noise. Now that that is gone, those road noises are unmasked. Therefore, they become prominent. There is also wind noise at lower frequencies. Those are like the buffeting noise when you have the window down by an inch or 2 inches or so. Those are low frequency sound. They become now very prominent because the internal combustion engine is gone. The electric vehicle's tonal noise, the gear whine noise, they become very critical. The buzz, squeak, and rattle, that sounds become very critical. So what is happening, it's like draining the lake. As I drain the lake, now I can see what is really there underneath at the bottom of the lake, and they're becoming of a concern. The magnitude is less, but the frequency contents are different and were masked before that we were not that used to hearing. Another thing that has become very important is the tire air cavity noise. We have had tubeless tires for quite some time, but the air cavity noise in the tire really did not become that critical since about 10 years ago when EV started becoming very attractive. So you will find what is happening is in that cavity between the rim and the tire, in that cavity, what we have is air, and that is causing some resonances. The resonant frequencies could vary from about 150 to 300 hertz, depending on the size of the tire, depending on the type of vehicles we are talking about, the load that falls in that area. And in here, inside, I don't know if you can see it or not clearly, but there is polyurethane foam absorption material. So by having absorption material, I can do something about that resonance. In this example, you can see this white material, that's my absorption material. Also, in some cases, people are using resonators. These are acoustic resonators that are actually on the rim facing the tire, and this is the wheel. So, and there are vents, openings, so it is designed that it will work best at a particular frequency. So if I know that at that frequency I have the air cavity resonance, I can use it. Autonomous vehicles can change the entire architecture. Now I have this young lady, she is enjoying her trip, doesn't have to worry about driving, no concerns, but the challenge is, are we remembering to take care of the safety features, plus many other types of noises that might come in? How do I address those? One of the benefits that might be in an autonomous vehicle, once it is fully engaged, when it's going to come, nobody really knows, but we may be able to do a lot of different things. And in that case, if we are doing some detailed work, the noise that comes in through the glazing system, that can become a nuisance, and therefore we have to address many of these things. Plus, the safety of the occupant, that's important too. The next few slides, it talks about there are different generations of this vehicle that we call autonomous vehicle or connected and autonomous vehicle. Fondly, it's called CAV. In this case, in this example, Waymo is a research organization that's working on these things. They have 40 different sensors. Do I need all of that? Possibly not. But at this time, in a fifth generation vehicle, there are 40 different sensors. Some of them are camera sensors. Some of them are radar sensors. Some of them are LiDAR sensors. The camera, it is an optical sensor that offers functionality analogous to our human eye. So it's like a regular camera simulates our eye, what we see. And if it is too dark, the camera will not be able to work. However, it will be able to give a colored picture. It will be able to give you the color detection. It will be able to tell you what kind of object it is. It will be able to tell you the lane tracking. So many of the things that we do with our eyes, it can do that. It will not be able to work in a bad weather, just like when it is bad weather, we don't like to drive. It cannot tell you about the velocity estimation. It cannot tell you anything about distance estimation. Then comes the radar. It's the object detection system that uses radio waves. It can tell you about the object, that there is an object, but it cannot tell you if the object is a human being or it's an animal, or what kind of object it is. Is that important? Um, in many cases, it could be very important. You certainly don't want to go and hit anything, whether it's a human being or not, but you need to know those things. So it can tell you the object, that there is an object, distance, velocity deduction or detection. It works in bad weather. It can detect the range, but it cannot tell you about the lane tracking, what kind of object it is, or angular resolution. So you can see some of the pluses here are actually minuses in this case. This is the LiDAR, which is the laser scanning approach. It reflects back to the image sensor, and it can detect the object. It can detect the distance. It also has a lot of angular resolution, but cannot tell you the lane tracking, production readiness, and few other things. So this slide shows the green means it is good for that. Yellow means it's medium. Red means it doesn't work. So in the camera, there are certain things that are very good. In the radar, there are certain other additional things that are very good, and some things that are the same as the camera. In the LiDAR, also the same thing. The point is, do I need to combine all of these and have a fusion? I may want to think so, but with the advancement, with the technology, with the opportunities, we may find that we can optimize the use of the camera, the radar, and the LiDAR. Okay, we can do in today's technology a lot of analysis, computation, electronics, and then we verify those things by making measurements to make sure all the predictions that I did, they are working good. Because at the end of the day, the vehicle that I own, I'm going to drive that vehicle. I'll be listening to that sound. I will not be predicting the sound anymore. Thank you. This is the end of my presentation, the webinar. Let me know if there are any questions. I will rely on Emily to see how we can get this thing done.
Yeah, so if you, like I said in the beginning, if you have any questions, please type it in the questions box for Pranav to answer. We did have a couple come through during your presentation. The first question is, why isn't there more concern about the external noise generated by the remote keyless entry? The remote keyless entry is noise, isn't it well above 70 dB? The noise isn't even desired by the owners. Owners never stand next to their vehicle to lock it. I see them walking away, sometimes a great distance before locking the vehicle. Why isn't there more effort to make the remote keyless entry less harsh?
This is a very good question. And what I can share with you is different OEMs think differently about these things. If you look at globally, there is an American culture, there is an European culture, there is I used to call it Japanese culture, but today possibly it'll be Japanese and Korean cultures together. Very soon the Chinese culture will blend to that. What I mean by that is, although between GM and Ford and Chrysler or Stellantis, there are differences in design, differences in NVH. But when you look at globally, you will find all the North American cars think more or less the same way. The keyless, the remote keyless entry, that's a big concern. If you think about it, how often do you use it? Once or twice during your travel from point A to point B. Some car companies, they pay a lot of attention to that. But the other thing is, you also want to use the alarm to be able to find the car in a busy parking lot. So where do you put the balance in? But I know one for sure, that a lot of OEMs put a lot of emphasis on how easily the door handle opens. Okay, how easily can you operate it? Because that's the first thing they feel when you go to a dealership place, you're going to do first. You're going to go and open the door. So the more easily the handle moves, they give more emphasis or quality to that. So likewise, I know that some of the keyless OEMs are working on the remote keyless keys. Next.
Okay, the next question, in a dissipative system, where does the energy go? Does the material heat up?
Another very good question. The material heats up, yes, but it doesn't heat up enough for any of us to worry. I want to give you a classic example. If 1,000 trumpet players, not 1,000, 100 trumpet players play in one environment, it's a lot of sound, it's noise, but it is hardly enough energy to raise the temperature of a cup of water by 1 degree Fahrenheit. So what I'm saying that yes, the energy goes inside the dissipative material and it gets dissipated there. So in theory, yes, the temperature of the fibers go up, but it doesn't go up enough to worry about it. I hope that helps. Next.
That's actually all the questions that we have. If anyone thinks of a question or needs to get a hold of Pranav to ask him anything, his email is on the slide, and the handouts are uploaded into the handouts box. Yeah. So that's all the time that we have. Pranav, thank you for a great presentation, and thank you everyone for joining us today.
You're welcome. And if you have any questions, just let me know. You have the email address. If you are really more interested to read more about sound package materials and vehicles, I have a book that I mentioned on the first slide. You can look at that. But otherwise, Emily and everyone else, thank you so much.
Yep, thanks. Bye, everyone.